Well, students, in this lecture, we'll continue our tutorial session on chapter number 2, exercise problems. Let me recall in one of the lectures, when we were defining significant digits, I told you that the meaning of this inequality will be clear from one of the exercise problems in chapter 2. I think it is the problem number 7, second subdivision. The problem is stated as follows. Show that the relative error in the floating point approximation of a given number x is less than or equal to 1 by 2 into 10 to the power of minus n plus 1 when this floating point approximation is obtained using n-digit rounding. Well, the problem was just restricted to decimals and therefore we have 10 here. However, this result is true for any base beta. Now, when you compare these two inequalities, you can see what is meant by this condition and what is the idea behind. If this condition is satisfied, then we say that the approximation, any kind of approximation, has or significant digits when compared to x, right? I hope you must have given a thought over all this and understood it. And I'm sure that you would have also solved this problem. But let me give you an outline of how to go ahead to solve this problem. The floating point representation of the number x is given by minus 1s into point d1, d2, and so on, dn, dn plus 1, and so on. It goes on like this. 10 into 10 to the power of e. Why 10? Because we are working with decimal. Now, FL of x is given by minus 1 to the power of s into point d1, d2 up to dn tilde 10 into 10 to the power of e. What is dn tilde? Dn tilde is equal to dn if 0 less than or equal to dn plus 1 is less than 5 and dn plus 1 if 5 is less than or equal to dn plus 1 is less than 10, right? So this is what we have as the definition of rounding, and we are given that FL of x is obtained by rounding x up to n decimal digits. So FL of x is given by this. Recall that this can also be written as minus 1 to the power of s into point d1, d2 up to dn plus 0.000 n minus 1 times and then 1 into 10 to the power of e if in the second case, that is dn plus 1 lies between 5 and 10, right? So just note this. Otherwise, it is just dn only, something like chopping. Keeping this in mind, let us consider two cases. Case 1 is when dn plus 1 lies between 0 and 5. In this case, x minus FL of x divided by mod x, that is what we want to estimate, and that is going to be equal to minus 1 to the power of 0 because we have taken modulus, but that I may not write it. We have point d1, d2, and so on, dn, dn plus 1, so on, right? Minus point d1, d2, so on up to dn, because it comes under the first case, both into 10 to the power of e divided by point d1, d2, it goes on, everywhere we have suffix 10, don't forget to write, into 10 to the power of e, right? So 10 to the power of e and 10 to the power of e will go off, and we will have 0.000 up to first n terms, because the first n digits in the mantissa coincides, and then we will have dn plus 1 at the n plus 1th digit, and then it goes on into 10 to the power of 0 divided by point d1, d2 and so on into 10 to the power of 0, and that can be written as point dn plus 1 and so on, 10 to the power of minus n divided by point d1, d2 and so on into 10 to the power of 0. There are two things that we have to note here. One is dn plus 1 is less than 5. That implies that point dn plus 1, and after that whatever may be the value of dn plus 2 and so on, surely this is the first term is less than 5, therefore this should be less than 0.5, right? This may be at the worst case 4, 9 and so on, right? So in which case also you have this is 0.5. And similarly, you take the mantissa in the denominator, that is going to be d1, d2 and so on. And remember that we have written x basically in the floating point representation. Therefore, your d1 is actually not equal to 0. So in the worst case, it can be something like 1 and so on. Therefore, it will be surely greater than or equal to 0.1. And that is going to be point d1, d2 and so on is going to be less than or equal to 1 by 0.1, and that can be written as 10, right? So putting these two inequalities in the above expression, we get x minus fl of x divided by mod x is going to be less than or equal to, the numerator is 0.5 into 10 to the power of minus n, and this term is less than or equal to 10. Therefore, I have plus 1 here. And this is precisely what we want to show, that this is half into 10 to the power of minus n plus 1, right? So that is what we have shown here. Let us consider the case 2 now. Here we have dn plus 1 lying between 5 and 10, right? So in this case, our floating point representation is written like this, and therefore, let's see how mod x minus fl of x divided by mod x will look like. That is going to be point d1, d2, dn plus 1 and so on. That is my x minus fl of x is going to be point d1, d2, dn plus 0.00 up to n minus 1 zeros. Then you have 1, right? All these are base 10, and everything together I will write as into 10 to the power of e divided by point d1, d2 and so on into 10 to the power of e, and as usual we will cancel 10 to the power of e, and we can see that this can be written as, and of course this also I can write as less than or equal to 10, the same idea as we did here, right? So I will write directly here less than or equal to. Now what comes here is the first n terms gets cancelled with this, and therefore we have 0.00 n times, and then you have dn plus 1 and so on minus 0.000, this is n minus 1 times 1, And remember, there is a modulus, so I should also write modulus in case if there is a minus sign coming, it will not come because basically we have taken modulus. So don't miss out that. 10 and into, already 10 to the power of e got cancelled. Now we got 1 power of 10 coming from here, 10 to the power of 1 because of the denominator. Therefore, I will have 10 to the power of 1, right? Here n number of zeros are there, but here only n minus 1 number of zeros are there. Therefore, what I will do is, I will take n minus 1 number of zeros, I will just cut and adjust it in 10 to the power. So we'll have 1 0 remaining here because there are n number of zeros. So it will be 0 dn plus 1, dn plus 2 and so on. But here I will have just 1 into 10 to the power of how many zeros I cancelled here? I have cancelled the n minus 1 number of zeros. Therefore, I will have minus n plus 1. Already 1 is there. Therefore, it is 2. So we got this, and you know that dn plus 1 is greater than or equal to 5, right? Therefore, 0.0 dn plus 1 and so on is going to be greater than or equal to 0.05, right? And now I am subtracting this from 0.1. So I am removing some number which is greater than 0.05 from 0.1. Therefore, I will have x minus FL of x divided by mod x will be less than or equal to 0.05 into 10 to the power of minus n plus 2, and that I can write as 0.5 into 10 to the power of minus n plus 1, right? So this is again what precisely we want to show. Next, let us do the problem number 13. In this problem, we have two numbers, x and y. X is negative and y is positive, and their approximations are given by xa and ya, where xa has 7 significant digits when compared to x, and ya has 9 significant digits when compared to y. Now we have to perform the calculation x minus y. We are asked to show that if we use approximate values instead of exact values, then we land up getting the answer which is 6 significant digits when compared to the true answer. So it means to show that mod z minus za divided by mod z should be less than or equal to 0.5 into 10 to the power of minus r plus 1. Now we want to have r to be 6, therefore minus 6 plus 1, therefore we want it to be minus 5, right? This is what we have to show. Let's calculate mod z minus za divided by mod z. That is going to be x minus y minus xa minus ya divided by the true value mod x minus y, right? That is just the definition, and this can be written as mod x minus xa divided by mod z plus mod y minus ya divided by mod z. I'm just using the triangle inequality. Now, given that x is negative and y is positive, therefore, we have z is equal to x minus y is greater than mod x, right? And also mod z is equal to mod x minus y, which is greater than mod y as well. Therefore, we can see that 1 by mod x is greater than 1 by mod z, and similarly The second one implies 1 by mod y is greater than 1 by mod z. Now substitute these values into our inequality. We get mod z minus za divided by mod z is less than or equal to mod x minus xa by mod x. I'm just replacing z 1 by z by 1 by x, and thereby I will have strict inequality plus y minus ya divided by mod y. The second inequality I am just applying and getting this. We are given that xa has 7 significant digits. Therefore, the first term is less than or equal to 0.5 into 10 to the power of minus 7 plus 1, that is minus 6. And the second term has 9 significant digits. Therefore, it is 0.5 into 10 to the power of minus 9 plus 1, that is minus 8. Now we have to add these two numbers. It is always convenient to put the exponent equal and then add to avoid the confusion. Therefore, I will write the same numbers as the first term I will keep as it is, and the second term I will write as 0.005 into 10 to the power of minus 6. Now I can comfortably add and get 0.5005 into 10 to the power of minus 6. But we want to get something like 0.5 into 10 to the power of some number, right? But we have something greater than 0.5 here. Therefore, what you can do is we have to get the nearest 0.5 number which can dominate this number, and that will happen to be 0.5. Well, I cannot write minus 6 because that will be less than this number. Therefore, I have to go for the next exponent, minus 5. This I can write, right? That is the best I can write because I have to have minus 5 here as per the definition. Therefore, this is the best I can dominate the given number 0.5005 into 10 to the power of minus 6. Once I have this, now I can see what is the significant digit. This should be minus r plus 1, right? From here I can get what is my r. R is equal to 6. Okay, so that implies that ZA has 6 significant digits when compared to the true value Z. Next, let us take 17th problem. Let xt be a real number and xa is an approximation to xt with an absolute error of at most 0.01. It means what? We are given mod xt minus xa is less than or equal to 0.01, right? That implies minus 0.01 is less than or equal to xt, which we don't know. We are not given xt, but xa is given to us, that is 2.5, and that is less than or equal to 0.01, right? So from here, we can just get 2.49 is less than or equal to xt is less than or equal to 2.51. So xt ranges from these two numbers. Now we have to evaluate f of x equal to x cube. Well, we want to evaluate at xt, but we are only given xa. Therefore, we can only evaluate f of x at xa, right? Now we have to estimate the resulting absolute error. That is, we want to find an upper bound for the absolute error mod f of xt minus f of xa, right? So estimate means we have to find the upper bound. You can also find lower bound if possible, but generally if I say just estimate, I expect only the upper bound. Otherwise, I will say find the range of this number, or find upper and lower bound, or find the interval in which this number belongs to, like that I will ask. Then you have to find both upper and lower bound. If I just say estimate, it means you just have to find the upper bound most. Now we have to find an upper bound for this. Remember, estimate means you have to find some number k which is constant and should not depend on both xt and xa, right? Now the question is how to arrive at such an upper bound. Well, the moment you write this, you get a clue that you may have to use the mean value theorem. Let's use this. Mean value theorem says that this can be written as f dash of xi, where xi is some unknown number between xt and xa, and this into xt minus xa. So this is what we can get from the mean value theorem, where xi lies between xt and xa, right? Now what is this? This is nothing but 3 times xi square modulus into 0.01 that is given to us here. Now you see what we can conclude from here about xi is the question, because this is the unknown. In order to get the right hand side a constant, we have to somehow get rid of this xi, right? So that is the only unknown sitting here. Now you can see that xt can be at most 2.51 and xa is already given to us as 2.5. Now whatever may be xi, it has to lie between these two. Okay, xt can be here also. Xt can go at most 2.49, right? Wherever xt is, you can see that xi has to lie between this, right? Therefore, what we can say is surely xi will be less than or equal to 2.51. That much we can say. Therefore, this is less than or equal to 3 into 2.51 square into 0.01, right? That is going to be 0.189003 in my calculation. You can check that. Finally, let us do this interesting problem. Check the stability of computing the function h of x equal to sine square x divided by 1 minus cos square x for values of x very close to 0. You can see that 1 minus cos square x is sine square x. Therefore, h of x should be equal to 1, whatever may be the value of x. However, we anticipate some problem near x equal to 0, because near x equal to 0, the denominator is 1 minus cos square x. Therefore, computationally, that is on a computer, we may not expect a good answer for this function. And that will be apparently seen in the stability analysis of computing this function. If you recall, the stability of evaluating a function can be decided by checking the condition number of each step involved in evaluating the function. So we have to first split this function evaluation into individual steps, and then we have to check the condition number of each of these steps. So what is the first step that we think that the computer will do? It will probably take some number x naught that is given to it, and it will find the number x1 which is given by sine x naught. Remember, x naught is given to us. The step 2 may be x2, which is nothing but x1 into x1. So that gives us the numerator. Now going to evaluate the denominator. Let's call this as step 3. When I ask you to study the stability, first you have to clearly write all the steps which are involved in evaluating the function. x3 can be cos x naught. Then step 4 is x4, which is x3 into x3. Then step 5 is x5 is equal to, once x4 is known, the computer will find 1 minus x4. So we got x2, which is the numerator, and x5, which is the denominator. Therefore, the final step, that is step 6, will be x2 divided by x5. So this is probably the step-by-step evaluation of the function when we split the function evaluation into individual operations. Now you can see that out of all these operations, we know that multiplication, which I have written here as star, and division, which is here, are well conditioned. We can check that. But from the examination point of view, multiplication, division, and addition, you need not check. If I ask you to only study the stability, if I ask you to check individually addition, then you may have to check. But if I just ask you to study the stability, then these three you can avoid. Now I'm going to do cos and sine. For step 1, take the function f1 of t is equal to sine t, right? So that is our step 1. The condition number for f1 is given by mod cos t divided by sine t into t, right? And we can see that that tends to 1 as t tends to 0. Why we are taking t tends to 0? Because we are asked to study the stability near 0 only. It means we want to give x very close to 0 and see how our computer will evaluate the value of h and gives us at that point. Okay, therefore our interest is very close to 0. That is why we are always trying to take the limit as t tends to 0. And since this is something which is bounded nicely, therefore we will declare that the step 1 is well conditioned near 0. Therefore, step 1 is well conditioned. So therefore, the step 1 is okay. Step 2 is multiplication, therefore it is okay, you can directly write. Step 4 is also multiplication, you can directly write. Step 6, you can directly write. Let us find the condition number for step 3. Let's take the function f3 of t is equal to cos t, and the condition number is given by mod minus sine t divided by cos t into t. Again, that tends to 0 as t tends to 0. So that is also fine. So this step is also good. We have to now check step 5. Of course, we know step 5 is the only bad part, because you can just see that anywhere subtraction comes, and if the two numbers which are subtracted, if they become very close to each other, then surely we have loss of significance happening in that computation, and that leads to the magnification of the relative error drastically. Okay, this is something which we know, but from the examination point of view, you have to write the answer like this. You are only allowed to directly write multiplication, addition, and division, whereas subtraction, you have to explicitly write the condition number and give the argument that it is going to be ill-conditioned near the point where we are interested in. In this case, it is the point 0. Okay. Remember, x4 is coming from cos, basically, right? X4 is basically cos square. Cos square x0. Therefore, when x0 goes to 0, x4 goes to 1. Therefore, it has problem. Okay, this step will have problem, but from the examination point of view, don't write it directly, but you write the condition number, check it and show. That is your exercise. So for step 5, take f5 of t is equal to 1 minus t, and the condition number is, and that is going to be t by 1 minus t, and that tends to infinity as t tends to 1, right? Equivalently, in our case, it is x tends to 0. Okay, x naught tending to 0, because our function t is, if you recall, it is cos x naught square. Okay, if you want, you can in bracket write. Therefore, f5 is ill conditioned in a neighborhood of 0. Okay, hence the process of evaluating the function h is unstable, because even one step is ill conditioned, the entire function becomes unstable. Here, although all the steps are good, but one step was bad, therefore the evaluation of h on a computer is unstable. That is the conclusion. Let me evaluate this function on my computer and show you how my computer struggles to handle this function very near to 0. I'm using Matlab. You can use any computing software that you are comfortable with. Let me first take x is equal to 1 and evaluate the function h is equal to sine square divided by 1 minus cos square. So you can see the output on this command window on the right of the screen. When you evaluate the function at x equal to 1, you can see that h as expected is given by 1. Now let me try to go very near to 0, say x is equal to 10 to the power of minus 5. There's a slight error involved in the computation, but still it is pretty good. Let me go much more closer to 0, say 10 to the power of minus 7. And now also the value is not exactly 1, but it is pretty close to 1. Let me go to minus 7.5 and see what is happening. And you can see that the error is progressively increasing. And now I'm going to go to 0.9, that is minus 7.9. You can see that there is almost a 30% error. And further, let me go to minus 7.97. And you can see that now h is shown to be 0.51, which almost has 50% error, right? Now, if I take 10 to the power of minus 8, I'm just computing using a single precision calculation, and therefore it just gives up completely and says the answer is infinity. That is because it just takes x as 0 and plugs it into the denominator and got it as 1 minus cos 0, which is 1 minus 1, that is 0. So the denominator became 0, and therefore it declared the value of h as infinity. So you can see that I have a pretty latest computer, and you can see how much it struggles to evaluate this small function as we go very close to 0. Although the function mathematically is a very well behaved function, but when you go to evaluate it on computer, it's very bad. Especially you can see the danger when I have evaluated 10 to the power of minus 7.97, the function value involved nearly 50% error. So if such calculations are involved in your model, then one has to be very careful, because your numerical method may be mathematically very accurate, but still, if any such situation occurs in the calculation, then without your knowledge, your computer may be doing huge error, which may result in a solution which is nowhere near to what you want. This is the danger of using the computers. As I told you earlier, computers are very powerful, but they have limitations. We have to understand the limitations and carefully use them. Otherwise, even a mathematically accurate problem may give results which are no way near to what we want, and that may lead to disasters.